In this video, we'll examine the force generated by drag. The total drag felt by an aeroplane can be divided into two parts. Zero lift drag, drag which is produced just by a function of moving an aircraft through the air, and lift dependent drag, the drag which we generate as a result of the lift that we are generating on the wings. Zero lift drag is split down into several components: surface friction drag, form drag, and interference drag. Lift dependent drag is also split into components which are induced drag and increments of the zero lift drag. Let's look at each of these forms of drag in a bit more detail. So firstly, zero lift drag. The act of moving an aircraft through the air in itself produces a certain amount of drag. This is because air is viscous, it is slightly sticky and wants to cling to the surface of the aeroplane. The magnitude of the surface friction drag will be dependent on a number of factors, such as the smoothness of the finish of the aircraft, whether we've accumulated any ice on the airframe, the total surface area of the aircraft, how big are we, and do we have anything like rivets or any other appendages which are going to cause a larger boundary layer, the layer of air which is feeling this surface friction drag. The second form of zero lift drag is form drag. As we push an object through the air, the frontal surface area will cause a resistance of the air as the air is forced to move out of the way. And the third component of zero lift drag is interference drag. It's noted that the total zero lift drag is greater than the sum of the parts. That is to say that if we were to add up all of the little increments of form drag and surface friction drag over the whole of the aeroplane, we'd actually note that it is less than the total quantity of zero lift drag that we have experienced. And this is because as the wings join the fuselage, or we have any meeting of two parts of the aircraft, the quantity of air which is affected by the surface friction drag and the form drag across those two components will be slightly larger. This is due to the interference between the boundary layers on different components. These three components, the total zero lift drag, is always present when an aircraft or any other object moves through the air, and it is proportional to the square of the speed. This means if we plot a graph of the coefficient of drag, the total amount of drag, versus airspeed, we will see that it rises exponentially as we increase our speed. So for a doubling of speed, we'll see a quadrupling of the zero lift drag. Moving on to lift dependent drag, we said it was split into two components. The first of these is induced drag. Now I'm a bear of very little brain, and I like to simplify things in my mind to have a conceptual model which I can really use. So I think of this as when a wing is producing lift, the lift vector will act perpendicular to the surface of the wing, and this is denoted by the green arrow on this diagram. The useful component of that lift vector is the blue arrow, the bit which is pointing directly up, for this is what's going to counter the weight of the aircraft. However, there is also a component of this green arrow, this vector of the lift, which is acting towards the tail of the aircraft and is effectively going to be acting as drag. If you can think of induced drag in these terms, you can imagine that as we increase our angle of attack, and therefore the amount of lift that we're generating, this green arrow will be angled further and further backwards, and therefore the magnitude of that red arrow that we're seeing here will be greater. The other big factor in this induced drag part of our lift dependent drag are the vortices generated from the wingtips. If we take our aircraft, we said that there was a slightly greater air pressure below the wings than above the wings. Now as we look at the wingtips on this aircraft, you can see that we have a pressure differential and the air wants to wrap itself round from the bottom surface over to the top surface in order to equalise the pressure. Now this rolling over of the air from the bottom surface of the wing to the top surface of the wing creates the wingtip vortices. The effect of these wing vortices is that they generate an area of descending air behind an aircraft. This downwash takes away slightly from our angle of attack. And I've depicted this by the red line here. The descending air, which is coming from behind the wing, is effectively eating into the angle that we had between the relative airflow and our mean chord line of the aircraft. Therefore, to get the same quantity of lift, we need to slightly increase the angle of attack further to achieve the same effect, thereby increasing the effect of the induced drag. Now, the other component of the lift-dependent drag, we said, was the increment of zero lift drag. This we can explain quite simply by looking at the following diagram. If you consider the frontal area of an aeroplane in a normal cruising configuration, it will take up a certain frontal area of air which will need to be pushed out of the way. As we increase the angle of attack, as we increase the lift being generated by the wings, that frontal area will increase by the fact that we are now presenting more of the form of the aeroplane into the airflow. What we can see from these two components of the lift-dependent drag is that as we are producing more lift, we will actually be increasing the amount of drag. If we take the same graph that we drew for zero lift drag and plot the coefficient of drag, the amount of drag, versus the airspeed, we'll actually see that as we increase our airspeed, so we can reduce our angle of attack, and therefore the drag caused by lift is decreasing. Let's now take a look at the total effect of this drag. What we saw was that we had the zero lift drag, which would increase as we increased airspeed. And we have the lift dependent drag, which will decrease as we increase airspeed. Adding the two components of drag together, we come out with this red line, which is the total drag. The lowest point in this line is VIMD, or minimum drag speed, otherwise known as lift over drag max. So for every aeroplane, we will have a speed at which we can fly where the drag on the aircraft will be at its minimum. If we are faster than the minimum drag speed, if we increase our speed by a few knots, the drag will increase. And this will tend to slow us down again, assuming that we have a constant thrust setting. Therefore, we can say in this portion of the drag curve, faster than the minimum drag speed, we will be speed stable. However, if we are flying slower than the minimum drag speed on the left-hand side of this curve, then you can see that if we were to decrease our speed, the drag will go up. The effect that this has is that with an increase in drag, we will tend to slow down further. As we slow down further, so the drag will go up, and so we will tend to slow down further. The speed will become divergent, or we can say we will be speed unstable. The effect that this total drag has on the aircraft is very marked, and we will refer back to this graph a number of times. We'll now move on to looking at the other forces acting on an aircraft in flight.